Welcome to the presentation entitled The Nature of Science. I am Dr. Jillian Wendt of the University of the District of Columbia. This presentation is an adaptation of a presentation provided by Rebecca Musso of Stafford County Public Schools at the Virginia Association of Science Teachers 2016 Professional Development Institute held in Williamsburg, Virginia, and is adapted and used with permission. In this presentation, we will discuss the basic tenets of the nature of science, or NOS. The basic tenets of the nature of science, or NOS, are as follows. Scientific endeavors set out to explain the natural world. Scientific ideas are durable, yet subject to change. Science cannot provide complete answers to all questions. Science demands evidence. Science is a blend of logic and imagination. Science explains and predicts. Scientists try to identify and to avoid bias. Science is not authoritarian, and science is a complex social activity. Let's take a look at each tenet in more depth. With the natural world is understandable. As the American Association for the Advancement of Science, or AAAS, states in Science for All Americans, a key science education text, science presumes that the things and events in the universe occur in consistent patterns that are comprehensible through careful, systematic study. Scientists believe that through the use of the intellect and with the aid of instruments that extend the senses, people can discover patterns in all of nature. Science also assumes that the universe is, as its name implies, a vast single system in which the basic rules are everywhere the same. Knowledge gained from studying one part of the universe is applicable to other parts. For instance, the same principles of motion and gravitation that explain the motion of falling objects on the surface of the Earth also explain the motion of the Moon and the planets. With some modifications over the years, the same principles of motion have applied to other forces and to the motion of everything, from the smallest nuclear particles to the most massive stars, from sailboats to space vehicles, from bullets to light rays. It is important that we teach students to consider and to recognize patterns. This is important as knowledge gained from studying one part of the universe is applicable to other parts. For example, as mentioned in the previous slide, the same principles of motion and gravitation that explain the motion of falling objects on the surface of the Earth also explain the motion of the Moon and the planets. The recognition of these patterns may seem second nature or rather obvious to us, but are something that must be explicitly taught to young learners, especially those at the elementary and middle school levels. Scientific ideas are durable. AAAS supports that although scientists reject the notion of attaining absolute truth and accept some uncertainty as part of nature, most scientific knowledge is durable. The modification of ideas, rather than their outright rejection, is the norm in science, as powerful constructs tend to survive and grow more precise and to become widely accepted. For example, in formulating the theory of relativity, Albert Einstein did not discard the Newtonian laws of motion, but rather showed them to be only an approximation of limited application within a more general concept. The National Aeronautics and Space Administration uses Newtonian mechanics, for instance, in calculating satellite trajectories. Moreover, the growing ability of scientists to make accurate predictions about natural phenomena provides convincing evidence that we really are gaining in our understanding of how the world works. Continuity and stability are as characteristic of science as change is, and confidence is as prevalent as tentativeness. Scientific ideas are subject to change. AAAS further supports that science is a process for producing knowledge. The process depends both on making careful observations of phenomena and on inventing theories for making sense out of those observations. Change in knowledge is inevitable because new observations may challenge prevailing theories. No matter how well one theory explains a set of observations, it is possible that another theory may fit just as well or better, or may fit a still wider range of observations. In science, the testing and improving and occasional discarding of theories, whether new or old, go on all the time. Scientists assume that even if there is no way to secure complete and absolute truth, increasingly accurate approximations can be made to account for the world and how it works. In order to assist students in understanding that scientific ideas are durable yet subject to change, it is important to help them recognize that scientists reject the notion of attaining absolute truth. In other words, scientists accept some uncertainty as part of nature, and thus modify ideas rather than outright rejecting ideas. For instance, Pluto was not rejected as being a planetary body altogether. Rather, Pluto was reclassified as a dwarf planet. Rather than rejecting the idea that planets orbit the Sun, scientists with new knowledge modified that idea and recognized that extrasolar planets or exoplanets exist that orbit stars other than the Sun. And the atomic theory has gone through multiple revisions and, in the face of new evidence and critical scholars, continues to do so. Hold misconceptions, however, such as scientific knowledge is fact without question. You can address these misconceptions by explaining how you understand how people a long time ago might have thought something was true based on the evidence that they had available to them at the time. But now, in light of new evidence, we know what is true. A good activity that can be used to bring this home for students is the mystery box activity. In the mystery box activity, the teacher places objects in a box in which students can reach but cannot see. Students are asked to use one sense, such as sound, to determine what is in the box and to record their guesses. Then, students add another sense, such as touch, to determine what is in the box and to record their guesses. This goes on and on with the idea that students' ideas of what might be in the box changed based on the new knowledge that they have gained. This, of course, can be likened to how scientists use evidence to determine scientific knowledge, but as new evidence comes to light, these ideas may be modified. Cannot provide complete answers to all questions. AAAS states that there are many matters that cannot usefully be examined in a scientific way. There are, for instance, beliefs that, by their very nature, cannot be proved or disproved, such as the existence of supernatural powers and beings or the true purposes of life. In other cases, a scientific approach that may be valid is likely to be rejected as irrelevant by people who hold to certain beliefs, such as in miracles, fortune-telling, astrology, and superstition. Nor do scientists have the means to settle issues considering good and evil, although they can sometimes contribute to the discussion of such issues by identifying the likely consequences of particular actions, which may be helpful in weighing alternatives. Misconceptions that students might hold include that science is fact no matter what, and that science can explain everything. We know that these ideas are not true. To further combat these misconceptions, be willing to say to students, "We don't know." No one can know for sure. Scientists are still researching this. Why do you think we don't know? How would you go about finding out? As you are all well aware, but is often necessary to pointedly share with students, there are many things about this world that we don't know and that science cannot explain. Scientific knowledge is derived from data and evidence gathered by observation or experimentation. As AAAS states, sooner or later, the validity of scientific claims is settled by referring to observations of phenomena. Hence, scientists concentrate on getting accurate data. Such evidence is obtained by observations and measurements taken in situations that range from natural settings, such as a forest, to completely contrived ones, such as the laboratory. To make their observations, scientists use their own senses, instruments, such as microscopes, that enhance those senses, and instruments that tap characteristics quite different from what humans can sense, such as magnetic fields. Scientists observe passively earthquakes, bird migrations, make collections, rocks, shells, and actively probe the world, as by boring into the Earth's crust or administering experimental medicines. Further supports that in some circumstances, scientists can control conditions deliberately and precisely to obtain their evidence. They may, for example, control the temperature, change the concentration of chemicals, or choose which organisms mate with which others. By varying just one condition at a time, they can hope to identify its exclusive effects on what happens, uncomplicated by changes in other conditions. Often, however, control of conditions may be impractical, as in studying stars, or unethical, as in studying people, or likely to distort the natural phenomena, as in studying wild animals in captivity. In such cases, observations have to be made over a sufficiently wide range of naturally occurring conditions to infer what the influence of various factors might be. Because of this reliance on evidence, great value is placed on the development of better instruments and techniques of observation, and the findings of any one investigator or group are usually checked by others. To assist students in understanding this tenet, it is important that they are repeatedly exposed to both qualitative and quantitative data, from gathering their own data, to interpreting data, to sharing data, to validating data. Importantly, students need to be explicitly taught why it is important to validate data through multiple trials and multiple data sources, also known as triangulation. Misconceptions that students might hold include the following. There is one scientific method. They tend to forget about human and instrumental error. You only have to repeat an experiment 3 times. And if I read it, it must be true. The doing science activity is a good activity to utilize to get this point across. In the doing science activity, students' ideas are elicited about doing scientific investigations. The activity is designed to find out if students recognize that scientists investigate the natural world in a variety of ways, depending on the question they pose, and that there is no fixed sequence of steps called the scientific method that all scientists use and follow rigidly. Other ways to combat students' misconceptions are through discussions before, during, and after lab activities. You might ask, what can, or could have, or did go wrong in this experiment? How did that affect our data? How can we improve accuracy in this experiment? And give examples. For instance, geologists and physicists will have differing procedures, although both employ similar processes based on evidence. Science is a blend of logic and imagination. AAAS shares that although all sorts of imagination and thought may be used in coming up with hypotheses and theories, sooner or later scientific arguments must conform to the principles of logical reasoning, that is, to testing the validity of arguments by applying certain criteria of inference, demonstration, and common sense. Scientists may often disagree about the value of a particular piece of evidence, or about the appropriateness of particular assumptions that are made, and therefore disagree about what conclusions are justified. But they tend to agree about the principles of logical reasoning that connect evidence and assumptions with conclusions. Scientists do not work only with data and well-developed theories. Often they have only tentative hypotheses about the way things may be. Such hypotheses are widely used in science for choosing what data to pay attention to and what additional data to seek, and for guiding the interpretation of data. In fact, the process of formulating and testing hypotheses is one of the core activities of scientists. To be useful, a hypothesis should suggest what evidence would support it and what evidence would refute it. A hypothesis that cannot in principle be put to the test of evidence may be interesting, but it is not likely to be scientifically useful. Finally, the use of logic and the close examination of evidence are necessary, but not usually sufficient for the advancement of science. Scientific concepts do not emerge automatically from data or from any amount of analysis alone. Inventing hypotheses or theories to imagine how the world works and then figuring out how they can be put to the test of reality is as creative as writing poetry, composing music, or designing skyscrapers. Sometimes discoveries in science are made unexpectedly, even by accident. But knowledge and creative insight are usually required to recognize the meaning of the unexpected. Aspects of data that have been ignored by one scientist may lead to new discoveries by another. The key aspects of this tenet that should be taught to students then are that imagination and thought may be used in coming up with hypotheses and theories, and that scientific arguments must conform to the principles of logic. Misconceptions that students may hold include that scientists only use one method, that science is not creative, and that hypotheses are rigid. In order to combat these misconceptions, it is helpful to provide examples of really crazy ideas people had that were ridiculed and now are reality. For example, sending a man to the moon, the idea of flight, plate tectonics, and the sun is the center of the solar system, all of which were deemed implausible and somewhat crazy ideas in their respective times, but now are reality. Other activities that assist in combating these misconceptions include those which drive creativity, such as STEM activities. Additionally, the What is a Hypothesis probe can be very helpful. In the What is a Hypothesis probe, students are asked to mark statements which describe a hypothesis, and then to explain their definition of a hypothesis. This assists the teacher in identifying where students hold misconceptions and how these misconceptions might specifically be addressed. Science explains and predicts. AAAS supports that scientists strive to make sense of observations of phenomena by constructing explanations for them that use or are consistent with currently accepted scientific principles. Such explanations, theories, may be either sweeping or restricted, but they must be logically sound and incorporate a significant body of scientifically valid observations. The credibility of scientific theories often comes from their ability to show relationships among phenomena that previously seemed unrelated. The theory of moving continents, for example, has grown in credibility as it has shown relationships among such diverse phenomena as earthquakes, volcanoes, the match between types of fossils on different continents, the shapes of continents, and the contours of the ocean floors. Further, the essence of science is validation by observation, but it is not enough for scientific theories to fit only the observations that are already known. Theories should also fit additional observations that were not used in formulating the theories in the first place. That is, theories should have predictive power. Demonstrating the predictive power of a theory does not necessarily require the prediction of events in the future. The predictions may be about evidence from the past that has not yet been found or studied. A theory about the origins of human beings, for example, can be tested by new discoveries of human-like fossil remains. This approach is clearly necessary for reconstructing the events and the history of the Earth, or of the life forms on it. It is also necessary for the study of processes that usually occur very slowly, such as the building of mountains or the aging of stars. Stars, for example, evolve more slowly than we can usually observe. Theories of the evolution of stars, however, may predict unsuspected relationships between features of starlight that can then be sought in existing collections of data about stars. Thus, the takeaway that students must be taught is that scientists make sense of phenomena by constructing explanations for them that are consistent with currently accepted scientific principles, and that predictions may be about evidence from the past that has not yet been found or studied. Misconceptions that students might hold include that scientists can't be wrong. Additionally, students often struggle with distinguishing between observations and inference. Thus, in order to combat these misconceptions, it is helpful to show a variety of images and ask students to make both observations and inferences. It is also helpful to give students real-life examples of observations and inferences. Here is an example of an image that might be shown to students. In this example, you might ask students what has happened. They will likely tell you that a car accident has occurred. But did they actually see the car accident? Since they haven't, they are making an inference. You might then ask them what they observed that helped them make that inference. For instance, a mangled car in the intersection, or a man sitting on the side of the road. Real-life examples might include conversations around the following topics. How do you know there is wind if you can't see it? How do you know it's going to rain before you hear the forecast? How can someone predict the outcome of a game before it happens? Scientists try to identify and to avoid bias. AAAS supports that when faced with a claim that something is true, scientists respond by asking what evidence supports it. But scientific evidence can be biased in how the data are interpreted, in the recording or reporting of the data, or even in the choice of what data to consider in the first place. Scientists' nationality, sex, ethnic origin, age, political convictions, and so on may incline them to look for or emphasize one or another kind of evidence or interpretation. For example, for many years, the study of primates by male scientists focused on the competitive social behavior of males. Not until female scientists entered the field was the importance of female primates' community-building behavior recognized. Additionally, bias attributable to the investigator, the sample, the method, or the instrument may not be completely avoidable in every instance. The scientists want to know the possible sources of bias and how bias is likely to influence evidence. Scientists want and are expected to be as alert to possible bias in their own work as in that of other scientists, although such objectivity is not always achieved. One safeguard against undetected bias in an area of study is to have many different investigators or groups of investigators working on it. Thus, students need to be taught that scientists are expected to be as alert to possible bias in their own work as in that of other scientists. One way that they can do this is by having many different investigators working on the same problem. Another way is through peer review. Young students may not be familiar with these concepts. Thus, it is very important to discuss them and the importance of these safeguards in ensuring valid and reliable information, free of bias. Science is not authoritarian. AAAS states, it is appropriate in science, as elsewhere, to turn to knowledgeable sources of information and opinion, usually people who specialize in relevant disciplines. But esteemed authorities have been wrong many times in the history of science. In the long run, no scientist, however famous or highly placed, is empowered to decide for other scientists what is true, for none are believed by other scientists to have special access to the truth. There are no pre-established conclusions that scientists must reach on the basis of their investigations. Further, in the short run, new ideas that do not mesh well with mainstream ideas may encounter vigorous criticism, and scientists investigating such ideas may have difficulty obtaining support for their research. Indeed, challenges to new ideas are the legitimate business of science in building valid knowledge. Even the most prestigious scientists have occasionally refused to accept new theories, despite there being enough accumulated evidence to convince others. In the long run, however, theories are judged by their results. When someone comes up with a new or improved version that explains more phenomena or answers more important questions than the previous version, the new one eventually takes its place. The takeaway that students need to know here is that esteemed authorities have been wrong many times in the history of science. Aristotle is a good example. Misconceptions that students might hold include, well, my last teacher said, or it's a scientific fact, or that science trumps religion. Other student misconceptions often center around theories versus laws, including the hierarchy notion that theories become laws, and that laws identify naturally observable phenomena, whereas theories attempt to explain them. In order to combat these misconceptions, it is important to provide examples of how ideas changed with new knowledge. For instance, the cell theory, the atomic theory, models of the solar system, and quantum theories. Science is a complex social activity. AAAS states that scientific work involves many individuals doing many different kinds of work and goes on to some degree in all nations of the world. Men and women of all ethnic and national backgrounds participate in science and its applications. These people, scientists and engineers, mathematicians, physicians, technicians, computer programmers, librarians, and others, may focus on scientific knowledge either for its own sake or for a particular practical purpose, and they may be concerned with data gathering, theory building, instrument building, or communicating. As a social activity, science inevitably reflects social values and viewpoints. The history of economic theory, for example, has paralleled the development of ideas of social justice. At one time, economists considered the optimum wage for workers to be no more than what would just barely allow the workers to survive. Before the 20th century and well into it, women and people of color were essentially excluded from most of science by restrictions on their education and employment opportunities. The remarkable few who overcame those obstacles were even then likely to have their work belittled by the science establishment. The direction of scientific research is affected by informal influences within the culture of science itself, such as prevailing opinion on what questions are most interesting, or what methods of investigation are most likely to be fruitful. Elaborate processes involving scientists themselves have been developed to decide which research proposals receive funding, and committees of scientists regularly review progress in various disciplines to recommend general priorities for funding. Science goes on in many different settings. Scientists are employed by universities, hospitals, business and industry, government, independent research organizations, and scientific associations. They may work alone, in small groups, or as members of large research teams. Their places of work include classrooms, offices, laboratories, and natural field settings from space to the bottom of the sea. Because of the social nature of science, the dissemination of scientific information is crucial to its progress. Some scientists present their findings and theories in papers that are delivered at meetings or published in scientific journals. Those papers enable scientists to inform others about their work, to expose their ideas to criticism by other scientists, and of course, to stay abreast of scientific developments around the world. The advancement of information science, knowledge of the nature of information and its manipulation, and the development of information technologies, especially computer systems, affects all sciences. Those technologies speed up data collection, compilation, and analysis, make new kinds of analysis practical, and shorten the time between discovery and application. What students need to inherently understand is that scientific work involves many individuals doing many different kinds of work, and as a social activity, science inevitably reflects social values and viewpoints. Examples that can be provided to students include the space race, stem cell research, cancer research, and biological weapons research. Misconceptions that students may hold include that most of the work is done in the U.S. and that we don't share or partner with other countries. Another misconception is that once a discovery is made, it is deemed true and immediately shared with the public. In order to combat these misconceptions, it is helpful to share examples of multiple countries working together. For instance, the International Space Station or other space projects. Another example is that of peer review. This can be modeled by sharing and compiling class data for review. You are encouraged to seek out the resources provided to you on your screen, as well as other resources related to NOS, as there are a multitude of resources available to you. Special thanks again to Rebecca Musso for providing permission for adaptation and use of this presentation.